Voyager 2 is among the fastest and farthest man-made objects in human history, currently exploring interstellar space after a grand tour of the outer solar system. But it launched on a rocket that only had enough energy to take it to Jupiter. And that's not unique to Voyager. Quite a few other probes have this mysterious energy discrepancy. So this begs the question, where did this energy come from? How could these spacecraft possibly take advantage of more energy than they were launched with? The short answer is, clever trajectories that take advantage of a body's gravity to transfer some of its momentum into a spacecraft. These are what astronomicists call gravity assists. But short answers are unsatisfying, so let's think like a scientist, and through critical thinking and experimentation, derive exactly what a gravity assist is and how we can use them to explore the cosmos. Simulations are fantastic tools for conducting experiments that would be impractical in the physical world. So let's simulate, from Jupiter's rather than the Sun's point of view, what happens when we make a flyby, say to collect some data. As we would expect, our trajectory is altered by Jupiter's gravity, constantly pulling us towards its center. Also, notice how even though the probe's speed changes continuously, at any 2 points of equal altitude, the probe is at exactly the same speed, similar to a ballistic trajectory on Earth. That answers how we can use a flyby to change our direction, but it still doesn't answer how we can use one to gain more energy, rather than just redirect it. Perhaps we'll learn more from this interaction by looking at it from a different point of view. Since this model sees Jupiter as static, we can represent the Sun's perspective by putting horizontal vectors on the entire reference frame that account for Jupiter's tangential velocity around the Sun. Adding these vectors together reveals something amazing. From the Sun's perspective, our final speed is now greater than our initial speed. We've completed a gravity assist. The big idea is, gravity assists have drastically different effects on speed, depending on your frame of reference. It's important to note that gravity assists do actually alter the speed of Jupiter and other bodies, but at the scales of modern spacecraft, it's completely negligible. Gravity assists allow us to think of space exploration as less of a collection of orbits with fixed energy requirements, and more as a constantly changing web of gravitational superhighways. This is how mission planners for Voyager 2 fine-tuned a trajectory that would cascade into a flyby of every single outer planet for just a fraction of the rocket power it would normally take. Each Voyager probe carries a golden record, inscribed with music, images, and information about what it means to be human. They are our bottles, floating in the cosmic ocean. These records, and the incredible journeys they've taken, are the epitome of human nature, exemplifying what we can accomplish by thinking not of how far we can go alone, but rather the seemingly impossible things we can accomplish with just a small change in perspective and a lot of teamwork. Thanks for watching.